Ever wondered how you click on a photo from a server halfway across the world and bam, it just appears on your screen in a split second? Well, it's not magic. It's something way cooler. It's all thanks to the internet's fundamental building block, the packet. Today, we're going to tear one of these digital packages open, the IPv4 Datagram, and see exactly what makes the internet tick.
Welcome to Super Courseva. Unlock the secrets of the internet and master computer networking. Let's dive in.
Okay, so here's the game plan. We're going to start with a really simple analogy, a nesting doll, to get our heads around the basic concept. Then we'll actually open up that doll to look at its shipping manifest, which is the header. From there, we'll see how it acts like a traffic cop for the entire internet, and finally, we'll put it all together to see how this whole thing brings a simple picture right to your screen. So to really get a grip on how data moves across the internet, you first have to understand how it's packaged. And you know what? The absolute best analogy for this is a set of those Russian nesting dolls. It perfectly shows us this core networking concept called encapsulation. The big idea here is actually pretty genius, and it's simple when you think about it. Data isn't just blasted across the wires. Nope. It's carefully wrapped, layer by layer. Each outer layer is basically an envelope for the one inside it, adding new instructions for each step of the journey. For what we're talking about, we're really focused on three main dolls. The tiniest doll, way on the inside, that holds your actual data, a chunk of an image, part of an email. We call that the TCP or UDP segment. That little doll gets tucked inside the middle one, and this is our star today, the IP Datagram, which handles the global addressing. And finally, the whole thing gets placed inside the biggest doll, the Ethernet frame, which is kind of like a local courier that only handles the very first leg of the trip. All right, you ready? Let's crack open that middle doll, the IP Datagram, and take a good look at its shipping manifest. This is the IP header, and trust me, this is where all the real magic happens. Seriously, stop and think about that for a second. Just 20 bytes. That's it. All the critical instructions needed for a little packet of data to navigate the entire global internet are squeezed into that tiny space. It's an absolutely incredible feat of efficiency. It's got everything a router needs to know to get that packet one step closer to where it's going. Okay, let's quickly run through the greatest hits here. The version field? That just tells the router which language to speak, the old IPv4 or the newer IPv6. The source and destination IPs? Well, you know these. They are the from and to addresses on our digital envelope. The protocol field gives a heads up to the receiving computer about what's inside the next doll. And the checksum? That's just a quick little math problem to make sure the header didn't get scrambled along the way. And this is where it gets really clever. See, not all data gets the same treatment. The service type field is basically a VIP badge. It lets a router know, hey, this packet is for a video call. It needs to get in the fast lane right now. Meanwhile, something like an email, well, it can take the scenic route. That prioritization is what makes things like video calls and online gaming even possible. But this header, it isn't just a mailing label. Nope, it's a full-on problem-solving toolkit. It's the internet's real-time traffic control system, and it's designed to solve some pretty big problems as they happen, on the fly. So let's throw our first problem at the header. Imagine our little packet is just humming along, and then it hits a part of the network where the road gets narrower. The connection can't handle a packet that big. It's like a semi-truck trying to squeeze through a tiny tunnel. So what happens? So does it just give up and go home? No way! The network is smarter than that. The router simply chops the big packet into smaller pieces that can fit. We call this fragmentation. And the crucial part is, the IP header has all the info the computer on the other end needs to put these pieces back together perfectly, just like finishing a jigsaw puzzle. And how does it do this without losing any pieces? Well, three little fields act like the instructions on the puzzle box. The identification field is like the picture on the box. It tells the receiver, hey, all these little pieces, they belong to the same puzzle. The flags field basically asks, is it okay to even chop this thing up? And the fragment offset is the most important. It's like a number on the back of each puzzle piece that says, I'm piece number 3. So the computer knows exactly where it fits. Okay, but what about an even scarier problem? A much more dangerous one. What if a bad setting on a router sends a packet from router A to router B, but then router B mistakenly sends it right back to A? It could get stuck in a loop forever, creating a zombie packet that just bounces back and forth, clogging up the whole network. Which brings us to a part of the header with a name that, I'm not kidding, sounds like a B-list sci-fi movie. But this little field literally saves the internet from collapsing on itself. And that field is called Time to Live, or TTL. But here's the twist, and this is super important. It has nothing to do with time. not seconds, not minutes. Think of it as a hop counter. It's a self-destruct sequence that ticks down every time it passes through a router. So a packet usually rolls off the assembly line with a TTL of, say, 64. As soon as it leaves your computer, the countdown is on. The first router it hits subtracts 1, making it 63. The next one makes it 62. You get the idea. So if our packet gets stuck in that loop, that number just keeps ticking down with every pass. 5, 4, 3, 2, 1, until a router gets the packet and sees the TTL as 1. It subtracts 1, the count hits 0, and bam, the router's only instruction is to destroy that packet. End of the line. And just like that, the zombie packet problem is solved. It's this simple, elegant, self-cleaning system that keeps the whole internet from grinding to a halt under the weight of lost data. It's absolutely essential. Okay, so we've looked at the dolls, we've read the manifest. Now let's zoom all the way back out and see the whole magic trick, the Matryoshka effect in action, bringing a simple picture from a server to your computer. So check it out. Here's the whole journey, start to finish. First, the raw data for your picture gets wrapped in a TCP segment. Then, that segment gets tucked inside our IP datagram with its 20-byte shipping manifest. For the very local part of the trip, it gets wrapped one more time in an Ethernet frame. And finally, the whole package is turned into little pulses of light or electricity and shot across the wires. And the wildest part? This isn't some rare thing. This whole complex dance of wrapping and unwrapping, it's happening for everything you do online. Every email you send, every video you watch, every single letter you type in a chat, it's all being packaged, shipped, and delivered using this exact system, billions and billions of times a minute. So yeah, the next time you're just casually scrolling, take a second to think about the millions upon millions of these tiny digital messengers racing around with their self-destruct timers just to bring that content to you. It really gets you thinking, right? What other invisible, amazing systems are out there, just quietly running our entire world?